You're gonna make us come in on Friday?
No, not Friday. Please be quiet, okay? I hear that you guys, many of you guys might have time on Tuesday. Right, you guys? No. Tuesday morning, I mean.
You should record the lecture and send it to us.
I know the kinetics were finished by 3:30, right? 3 o'clock? Okay, yeah, with that.
You could do any Friday that Dr. Chauhan doesn't teach during the lecture then.
Oh, that's a good idea.
Periods then.
What's the time?
It's from 3 to 5.
3 to 5? So he's not teaching every day?
He doesn't teach every Friday.
Oh, good. Okay. Then that would be a good choice. Yeah. I cannot hear you. Guys, please be quiet. I'm sorry, what? Yeah, but to post the video, I usually need to use the Edge facility. It's not that easy to get for this kind of standard class. I know. That will be one choice, but it's very difficult to arrange that. So I prefer to have a real, this kind of slide teaching. I saw some other question, comments. Oh, okay. It's hard. Tell you the truth, it will be very difficult. Okay, I need to find a room, but not that available. Okay, so, anyhow, the makeup of the Mason class were told maybe in November, so we don't need to worry too much about now. Today, what I'm going to do, I want to continue chapter 6, but I do not think I have time to finish it. So the first exam, which will be next week, tonight I will email you which sections will be covered in first exam. Okay, so not all, but part of the chapter 6, I am going to cover that one in the first exam. Okay. First exam, chapter 2 not included, so we have chapter 3, 4, 5, and part of 6. Okay, so I will have, we will have some multi-choice problems. So you will pick up, force or true, those kind of questions, followed by, say, some real calculations. Okay, so, but the good thing for the exam is you guys are allowed to bring 1 page of cheating sheets, right? So you can write your formula there. So it will, I think it should be fine. So the difficulty level should be similar to the quizzes. Today you will experience the second quiz, so I don't think it will be significantly harder than that. So yes.
So the general radius of metals and stuff you'll provide in the table.
Yeah, if there's, you don't need to remember any constants or any, say, for example, size of atoms. No, even for me, I cannot remember that. If there's anything needed, you should be able to find it in the exam. Okay, I should provide that. Any other question? Yes. You can return, during the break or holiday. So once again, I'm going to continue chapter 6, and then we will have 5 minutes break, and then we will start the second lecture. I will give it about 25 minutes left. Okay, so we will finish at about 6:25. This chapter, as I mentioned, is really important chapter. Okay, so that's the core material of material science and engineering, which is as important as chapter 3. Okay, like a crystal structure. So there, in the last class, I didn't see many of you guys, so I want to go over. Okay, I have to go over, otherwise many of you guys won't pick up. So the last class when we talk about, first we talk about several different ways for processing metals, right? Like a casting, directly casting, and we talk about the rolling, right? Rolling is very important. We have two different ways for rolling, right? One is at high temperature. So that means when we heat up the metal to above, usually above a temperature called recrystallization temperature. Okay, I am going to cover that one. That's a very important concept. I'm going to recover that one in next class, okay? So after the first exam. So usually when the temperature of your metal is above the recrystallization temperature, or that means when the metal is hot, you can imagine that the mechanical property or the mechanical strength will be reduced. Guys, please keep quiet, okay? So by that one, when you apply stress onto the metal piece, then you can easily see that you can greatly reduce the thickness, right? Because the metal becomes soft at high temperature. So we call that one hot rolling. At the same time, hot rolling, you need to heat up. There's a lot of energy requirement. But you can actually also do the rolling process at a lower temperature, or sometimes even at a room temperature. Okay, so we usually call this cold work, because we do work on the metal piece. So by that means you applying a very high pressure. The reason why you need to do that is because the metal is really rigid at room temperature. You need to apply in a high pressure to significantly reduce the thickness, right? Easy to understand. So, but that process is very important. We call it cold rolling, or many times we call that cold work. Okay, cold work means we have done some work to the metal piece, and then we input some energy. Some energy will be stored in the finally deformed metal piece. Okay, so where this energy will go? Where is this excess energy will go? What do you guys think? It reduces the thickness, but it must be some of this cold work will be stored inside the metal piece, right? What do you think? What do you think this energy will be dissipated inside the metal under the cold work or the cold rolling? What do you think? Where do they store? That's a very important concept, okay? What do you guys think? Yeah, usually this kind of a cold work will be stored by generating more defects, right? So usually you will see after this kind of a cold rolling or the cold work, there's much more defects, density of defects in the cold work metals. So that means after the field becomes thinner, you store excess energy inside that through what? Through the generation of new defects. Usually dislocations, grain boundaries, and many others. Okay, that's an important concept. Okay, so after the cold rolling, cold work, energy will be stored inside the metal through generating more defects. Okay, and this kind of like a process, related to the reduction. You usually do a multi-stage of reduction, right, in the thickness. And in addition to the rolling, you can also think about extrusion, right? That's another important process. Extrusion is a very important later when we talk about the polymers. Many of the polymers are actually being processed this way, okay? And the forging, like hammering, right? That's also very old technology to make the film of the metal become thinner and thinner. So you can also generate more complex shape. And once actually in this chapter, we will introduce quite a lot, many different, percentage quantities, okay, that will indicate the different property of the metals. One is, during the drawing process, we define the first percentage quantity, we call that percentage code reduction. That one is what? It's the change in the cross-sectional area. So that means the final cross-sectional area of your, code, the wire, during the wire drawing process minus the initial one divided by the original area times the 100%. Okay, so that indicates how much, code work or those kind of wiring process you apply to the metal. Okay, and then last class we start to talk about the deformation, right? Because we introduce two different deformation when you applying a force or a stress, onto, say, for example, a metal piece. These times indicate by applying a tensile stress. right? So it's the force you applied is parallel to the long axis of your metal rod. In this process, in the deformation process, we know that there are two different processes occur here, right? One is called the elastic deformation. So think about the spring, okay? Comparison of the spring. Elastic deformation means when you drag the spring to a certain distance, when the distance is not that large, when you release the spring, they go back to the original conformation, right? So that means the plastic deformation means what? Means once the external stress is released, the atoms, or the atoms in the metal, in this chapter, we mostly focus on metals, okay? But the same concept can be applied to ceramics, to polymers, to all the other materials, okay? So when you just release the stress, the metal atoms actually going back to their original location before you apply the stress, right? So that's called the elastic deformation. And if the stress is too high, okay, so that means the metal atoms undergo some permanent change. Okay, so their location will be fixed there. Even you release the stress, the atom position will not go back to the original one. We call this deformation plastic deformation. Okay, so that means something permanently happens here. Okay, usually from the atomic level structure, if you think about that, is the elastic deformation means the atomic rearrangement can go back to their original state, but the plastic deformation cannot. Okay, so the deformation is too large. The magnitude of deformation is too large. And then last class we defined two important parameters here, right? One is called the engineering stress. Stress, if you take a look of the unit of the stress, it's a Pascal or PSI. It's a pressure. Okay, so that means when we talk about stress, it is a force over area, right? So that will give you a pressure unit. So we define the engineering stress as what? As the force. See, for example, if we talk about the tensile stress, we talk about the tensile force. That means when you apply a force parallel to the long axis of your rod. Okay, so that force divided by the cross-sectional area of the original cross-sectional area of the rod. Okay, so engineering. So here I define engineering stress. Engineering stress is force over the original cross-sectional area. Okay, this is very important. This is a concept actually, correlated with only the original one. But don't forget, during the deformation stage, or when you apply a higher and higher force to your sample, the cross-sectional area will become smaller and smaller. Right? Don't forget. But when we define the engineering stress, we do not consider this kind of a narrowing of your sample. We only use the original cross-sectional area in calculating the engineering stress. Okay? But anyhow, this is the engineering stress. And another important is the engineering strain. Engineering strain we define that one as a delta L. Delta L means how much change in the length of your rod over the original length. Once again, don't forget, when we talk about the engineering stress, we talk about the original length. Okay, so it's a delta L over L, and indeed the unit of the strain you can think about, they can have the original length and the difference in length and the original length, like an inch per inch or meter per meter. But indeed the strain, engineering strain, you can think about it, it's a dimensionless unit, right? It's a dimensional quantity. So it defines how much of the elongation occurs, right, during the deformation process. Or we can define that one, see, for example, 1% change, length change, 40% change, those are the strain. Strain indicates the length, the relative length change. Okay, it's a dimensionless unit. Strain, the stress is a pressure. Okay, it's a force over original cross-sectional area. Okay, so that's the engineering stress and the engineering strain. And the shear stress, you can also think about when you're applying a shear force, it's a force over area, but this is not that important. Okay? So, and in the real experiments, this is the kind of like the real experiments people use to determine the engineering stress and the engineering strain. Okay? So, from the definition here, if you think about, if you want to calculate the engineering stress, you need to know the force, right? Because A now is the cross-sectional area. That one is very easy to define, to measure, right? You can just use a caliper to measure like a diameter of your testing sample, and then you can calculate that one, right? So A now is a known number, okay? Force, in this case, we actually can use a load cell. This load cell, you can apply different forces, okay, through the load cell to your testing sample, okay? Your testing sample in this case is here, okay? You put the testing sample between two attaches and then applying a force. The force is applied through the load cell, okay? And then the computer actually can record this load cell. And then, because you know in this test sample, next slide I'm going to show you, the sample, the testing sample, dimension of that is well defined. Okay, usually we use a 1/2 inch diameter as the testing sample. So that means if you know the force applied through the load cell, we can calculate the A now, then we can easily calculate the engineering stress. Right? So that's an easy way to do. And another thing, if we want to define or you want to measure the engineering strain, that's also a quite easy job here by using the tensile stress tester. Okay, that one actually is measured by this extensometer. So by that means you just need to know how much change of your testing sample occurs during this tensile testing process. Right? So that by that way, if you know the final length and also we know the initial length, then we can easily calculate the engineering stress, right? So by that way, by using this tensile tester, we can easily measure, by applying different force, then we can measure this engineering stress versus engineering strain, right? Once again, engineering strain we define the engineering strain as the change of the specimen length divided by the original length, right? That's an easy term to define. So that means it's a percentage, right? See, for example, if you take a look of like this curve, this is for a metal. If you see 0.06, that means the sample undergo 6% of elongation during the test, right? So that's so that's the x-axis. Y-axis, in this case, the unit is a kilo psi, okay? And if you take a look of stress strain curve, you will notice that at the very beginning, at the starting stage, there's a linear range. Okay, so that means when you apply larger force, you will get a longer elongation. You will get a larger elongation. Okay, and then if you if you reverse the process, if you let the loading cell release the load, then if you let it going back to the zero load condition, what you will see the sample will go back to their original state. Okay, so it's more like an elastic, it's more like a rubber case. Okay, you can elongate that one, you can let that go over back to the original state. Okay, so for this kind of a linear section, what do you think? Do you think that will be the elastic deformation stage or the plastic deformation stage?
Elastic.
Definitely elastic, right? It's very easy to understand. It's an elastic state. So therefore, this stage is very important. Because using this stage, that stage, we can easily pick up, see for example, when the engineering stress is 70 kilo psi, you can then get the corresponding engineering strain, and then using this linear stage, we can calculate one important material